Okay. So last time we learned about the object detection pipeline. So this is one of the, representative computer vision application. The real images are composed of multiple objects inside. So to analyze the real images having multiple objects, we have to detect the objects with proper representation. And here in object detection, we are representing the objects with the bounding box. Okay, so we have to, properly capture the object location with the bounding box representation and have to classify the object inside this bounding box. And this is called as the object detection task. Okay. And we already learned about the segmentation task before, but the segmentation could be heavier than object detection, but somehow using the transpose convolution operation, there could be some easier solution for this. But object detection, in my opinion, this seems more complicated when implementing this in the deep learning architectures. Okay, so the naive way to extend the deep learning method towards the image classification based deep learning method towards the object detection, the naive way is to apply this kind of sliding window approach. Okay, so we already talked about this when extending the image classification towards the semantic segmentation. So we apply this type of windows in this manner. So until we meet the last pixels, we slide this kind of window and classify the regions inside this bounding box using the CNN architectures. That would be the most naive way to implement object detection. And also the object could be in different scales. So the humans are mostly in upright position, and the car is having maybe this type of shape. Okay, and maybe human face might be fit to the square. Okay, so anyways, the object have diverse shape. So we also have to apply this type of different bounding boxes as the sliding windows, maybe. So applying this multiple times may take a lot of time. So maybe if it takes more than few hours, more than maybe 4 hours, maybe, anyway, several hours to achieve this object detection task, it might be better for us to do it by ourselves without using AI. So this might be impractical. Okay, so the computer vision researchers are gradually thinking about how to improve this. But indeed, when using the classical machine learning algorithms, for example, in the year of 2001, for achieving the face detection, they indeed apply this kind of sliding window approach. Okay, so I already explained this. They classify region inside the sliding window by extracting some hand-engineered features whose name is heart-like feature. And then they classify this heart-like feature into face or non-face. They actually does the binary classification to achieve the face detection. Okay. Actually, their algorithm is called as boosting. They use boosting algorithm for classifying this region-wise feature. Okay. But I mean, applying this towards the CNN network takes a lot of time and it's impractical because the DNN, it has a lot of parameters. Also, it takes a lot of time. So first solution to make it efficient is we can select the bounding box. Instead of applying the bounding box in the sliding window manner, we can somehow make the selected, bounding boxes. Okay, so find image regions, bounding boxes that are likely to contain objects. Okay, that's the selective search method, and their aim is to filter out the bounding boxes which may not have the object inside and remain only 1,000 bounding boxes in a few seconds. This is their algorithm's objective, okay? So for example, given this RGB image, if we apply the selective search algorithm, we can get this amount of bounding boxes, which may contain the object. Okay. Without applying selective search algorithm, if this image size, let's assume the image size is like this, then there would be this would become the number of bounding boxes. And even if we consider the multi-scaleness of the objects, then we may multiply the number of window type, okay? This might be very large number, right? Maybe more than this number, okay? And if we use 10 types of windows, then the number might be very large. So if we filter out unnecessary bounding boxes, 1,000 bounding boxes, it's still large number, but compared to the sliding window number, this selective search bounding box, their number is quite small, okay? So maybe when using the same CNN algorithm, the speed might be 1,000 times faster than using the sliding window when we use the selective search algorithm. Okay, are you agree with this? Okay. So this is algorithm. Okay, so in selective search algorithm, they are assuming that they can select 1,000 bounding boxes which may contain object inside. But how to know they will contain the object inside? They are actually assuming that the same object may have same or coherent colors, textures, or other features. So I agree with this. So they first segment, this kind of maps are denoting that you can somehow cluster each pixels. So you can extract each pixel. So this pixel may have RGB value. So we can actually collect the pixel number wise this kind of three-dimensional vector. Okay, we can collect that. So from an image, if the image size is this, then we can collect samples from each pixels. And each pixel may contain RGB value. And after that, we can somehow cluster the similar colors, okay? And then you can get this type of clustering map. So this is meaning that the color itself does not mean anything, but if pixels are belonging to the same pixel, same color, then it means they are belonging to the same cluster. Okay, can you understand this? So there's some clustering method, okay, which may call as the K-means algorithm. But we are somehow assuming that you already know this, some of the clustering method. Anyways, by applying this kind of clustering algorithm, we can cluster each pixels using their color values, and we can get this type of segmentation map. Okay, so and each if the pixels color is same, then it is meaning that their actual RGB values are similar. Okay, so we can get by obtaining this kind of map information, we can get such information. And also this type of cluster, each cluster can be a bounding box. So before that, I have to explain that. So, and also in cluster, there's one hyperparameter. How many clusters we will get from this image. Actually, that is kind of heuristic parameters, and we can set it with multiple scales. So for example, here we said calculate 50 clusters from the RGB feature. And here we can say 200 clusters we have to make from the color features. Then, we can get over-segmented image for these color pixels. And also we can get the normal segmented image and also under-segmented image like that. So this is denoting that, okay? So this is from the same image, we can get over-segmented image and normal segmented image and under-segmented image, okay? So we don't know actually which might be the optimal for this image, but from this, at least each cluster is meaning that they are having the similar color, or also we can do this clustering for textures and other features as well. And anyways, we can get some cluster that is representing the coherent, representing the regions having coherent color, textures, or other features, okay? And we can map each region, from each region, we can get the bounding boxes that tightly surround these regions, okay? So these individual things are becoming the bounding box, each one becoming the bounding boxes. And actually, these bounding boxes are becoming one of the 1,000 bounding boxes, okay? And we assume that they are in selective search algorithm, they are assuming that if pixels are having coherent color or textures or some features, if they are coherent and they have some size, then that could be the region that may have the object inside, okay? And we select the 1,000 or 1,000 to 2,000 bounding boxes from an image using this type of information, okay? So their aim is actually these three. They try to capture all scale bounding boxes, and also they actually diversify how to cluster these maps using different features and different parameters. They diversify how to cluster. So they can get diverse, bounding box. And also this have to be fast to compute. So these actually three are the objective for getting bounding boxes using the selective search algorithm. Okay, are you guys following this? Okay, so maybe doing this type of under segmentation, over segmentation, or normal segmentation, from that we can calculate some cluster, and we can get some bounding boxes from those clusters. Okay, and also we can get some diverse these bounding boxes by involving diverse features and diverse hyperparameters. Okay, the selective search algorithm. And this is not that important. Somehow they also do some grouping between the over-segmented regions. So basically their algorithm is from the initial they have some initial regions. This is maybe the smallest segments. Okay, this R is meaning the smallest segment, and also they are merging some this smallest segment by calculating the similarity between two regions. Okay, and they are somehow merging to make the bigger segmentation regions, and S is actually storing such regions. And if some regions are very similar, they actually this is for calculating the similarity between the two neighboring regions. Okay, so this is the code for comparing all neighboring regions, Ri and Rj, which are neighbors, and we calculate similarity for every neighboring regions. So this is for calculating similarity for every pair, neighboring pairs. And until S is non-zero, we somehow find the pairs which may have the highest similarity, okay, and actually merge those two regions and remove those two from the original S, which contain the similarity between all pairs. And then, also they remove it for Ri, and they remove it for Rj. And they recalculate, this RT becomes the new region that merges this Ri and Rj. Okay, and they calculate the similarity between this new region and all others and merge them into this similarity and region index. Okay, so this is kind of the algorithm to merge very similar regions. Okay, they also apply this type of things when calculating the selective search algorithm. And also you can learn this selective search algorithm easily in the OpenCV library. So you can get actually this type of code, okay? And this is actually the code for learning the selective search algorithm on arbitrary images, and you can visualize it using this code, okay? This is loading the image, and this is applying some selective search algorithm, okay? Anyways, using this selective search algorithm, what researchers have done was they developed this regional CNN algorithm. Okay, so this RCNN was the representative deep learning architecture proposed for the object detection task. Okay, actually, this was the first algorithm for that could achieve the object detection task. And you may remember that in Leap's 12 paper, the AlexNet was proposed. And right after, I mean, a year after, the computer vision researchers proposed how to extend this type of ImageNet classification network towards the object detection task. Okay, and the result was developing this type of regional CNN algorithm. So how they operate, I will explain from now on. And given this input image, they first extract 1,000 to 2,000 bounding boxes using the selective search algorithm. Okay, so we just learned the selective search algorithm. And then what they do afterwards is they apply the ImageNet pre-trained CNNs on these regions. Okay, so if you apply these CNNs, if you apply these CNNs with the sliding window method, you may have to apply that H by W number of times. And if you have multiple window types, then also you have to multiply that time numbers as well. So the computation number, for applying CNN, you have to apply CNN this amount of time. But here they apply CNNs only for the selective search bounding box. So it is only 2,000. So actually also it is the constant value. So this is compared to this number, when we use the sliding window approach, this number greatly reduced. Okay, and for each region, you can also extract some vector which may represent some feature for each regional feature. And then after that, you can apply classical machine learning algorithm, the SVM, support vector machine. This is one of the classification algorithm having just one layer. So this is the shallow learning algorithm. So after getting some features using the CNN architecture, you apply support vector machine afterwards to map this feature to the semantic classes. Okay, so that was the regional CNN algorithm. Okay, are you guys following this? Okay, this regional CNN is becoming practical in time complexity because they greatly reduce the number of bounding boxes. Okay, but there are some limitations. Okay, they are still slow because they have to apply CNNs which have many parameters 2,000 times. So this is still slow. And also the other important thing is they are not end-to-end trainable. Okay, so especially this selective search algorithm, as you already seen, this involves the clustering algorithm to make some segmentation map. And after getting the segmentation map, you get bounding boxes from that. Okay, this operation is not differentiable. I agree with that. Okay, so extracting this bounding box from the images, that step is not differentiable. And after getting this bounding box, you use convolutional network, and afterwards you apply the SVM to map the features to the semantic class. So this step, after extracting these patches, this step could be differentiable. Okay, could be optimally trained using the gradient descent algorithm and involving some more data, maybe. But the previous step, extracting this cropped bounding box, that part is not differentiable. So, that is kind of suboptimal. This is meaning that they are not that optimal. Okay, this part extracting the bounding boxes that is not differentiable and handmade, not trained, so they are suboptimal. Okay, there's two limitations in RCNN algorithm. But the thing is, thanks to involving the CNN feature extractor in the middle, they are they are reporting the best accuracy compared to the shallow learning algorithms. Okay, that's why people are getting interested in this direction. Okay, so CNN in 2012, they reported as the state-of-the-art accuracy in image classification task. And afterwards, in the year of 2013, the researchers proposed the RCNN algorithm, which is the object detection algorithm. And they actually reported as the state-of-the-art for object detection algorithm. But they have some limitations like this. So in ICCB 2015, which is one of the top conference, in this venue, the fast RCNN algorithm had been proposed. So in the name, you can expect that that algorithm is faster than RCNN algorithm, okay? So their main innovation lies here. So previously, you saw that we extract this type of patches, okay? But you can imagine this kind of situation. If someone cropped this patch, and this patch, small patch, may have some object in it, right? Maybe some partial human in it. And we have to classify this into some into semantic classes, okay? This is easier case, but if the window looks like this, if the window is extracted from here, then it may have boundary and I don't know. These human objects are rather easy to tell it is the human, but some cropped images is not easy to tell what exactly is the object inside the bounding box. In that case, there could be some confusion, right? So, people, even humans, are not classifying these, classifying the objects, seeing only these cropped regions, but they see whole images, okay? They have to see whole images to say this region is having some object, okay? This kind of contextual information is essential for achieving the successful object detection, okay? I agree with that. But this RCNN is somehow doing this type of thing, giving only small patches to this network and request it to classify classes within the small patches. So this is kind of, we can do that in some case, but sometimes it is nonsense, okay? So similarly, because of that, there are some suboptimality as well in this extracting the sub-windows part, okay? Because that is the non-differentiable operation, we cannot further train, and also we cannot consider the overall whole images context, okay? But this ICCB paper, they are somehow, at first, maybe they are motivated to reduce the time complexity but may you will feel that this method is more plausible framework for achieving the object detection because they can fully use the context inherent in the whole image. So I will explain that. So they first apply the ImageNet pre-trained CNN architecture. I mean, CNNs are sometimes called as convolutional neural network, and we make it, we call it as ConvNet in short sometimes. Anyways, we apply the same ConvNet architecture on whole images instead of the small patches. We can apply it to whole images. Okay. I mean, you already learned about the convolutional operation. So what they do is just use this small filter kernel, and I mean, again, they do sliding window to element-wisely multiply the filter coefficients and image pixels and add them and calculate what the output pixels one by one. This is the convolution operation, right? So I mean, what dimension the input image is having? The only changes is the output map size. If we apply small patches as input to the convolution, then our output patch might be in the small scale. But if we apply whole image as the input to the convolution, then it may have the larger output, okay? And it happens here like this. So, I mean, when we apply this same convolution operation to whole images, what resulted is the 2D feature map. Okay, dimension reduced 2D feature map, we can obtain it from the whole image. Okay, but thing you have to remember is in the feature map, you can see that in convolutional result, these regions features are retained in somehow this region, and maybe this region's features are retained in this region. Okay, in the 2D feature map, when we apply the convolution operation, this region's feature, is extracted by convolving the, I mean, applying the multiplication with filter kernel values and also the pixel values nearby that pixels. So somehow these regions features are retaining information in these regions in input images, and also this region feature may contain the information in these input pixels. Okay, so somehow convolutional features, they are retaining the spatial information. Are you agree with this? Are you indeed agree with this? Okay. So we can say this region, their features are retained here, and this image pixels feature might be retained in these regions. Okay, these 2D feature maps are somehow resolving the spatial information. Okay, so their idea is instead of applying cropping at the image level, they applying convolutional network on these feature maps multiple times. Instead of doing that, they first apply feature extractor once, just one time, and extract this feature map, and then they apply the selective search bounding boxes, in this 2D feature map space. Okay, so because this region's feature might encode this region's input images, okay? And this region may encode the pixel information in these regions, okay? Because this 2D feature map is somehow retaining the spatial information instead of cropping the images in this image space. We can crop the extracted features using the selective search. Selective search bounding box, applying the selective search bounding boxes in this feature space, okay, instead of applying them in the input images, okay. Okay, but the thing is, the next problem is to apply, maybe if we can apply a selective search algorithm here, right, and we can extract feature patches like this, okay. But the thing is, their size, the window size could be varied, okay. But the thing is, after this, we will apply some MLP layers to transform these features into some one-dimensional feature or some, anyways, applying some differentiable operations like convolution or MLPs, we will transform it eventually to the class information, okay? So, I mean, these MLPs can deal with the fixed dimensional signal, okay? What I mean is, these MLPs are doing, for example, transforming 100-dimensional signal to 30-dimensional signal. So, I mean, what they can do is they can input fixed dimensional input and output the fixed dimensional output, okay? So, but the patches, feature patches extracted here is, their dimensions are varied, okay? And because of that, we use this ROI pooling method. This ROI pooling is a region of interest. This means some regions which we are having the interest in. So this ROI is meaning region of interest. We apply some pooling operation, and their operation looks like this. I mean, their objective is from the varied dimensional feature, extracted feature, we have to map it to fixed dimensional feature. Okay, that's the objective of this ROI pooling. Okay, to achieve that, you can assume, you can regard this as the cropped 2D feature. Okay, this is the cropped 2D feature. They are in the varied dimension. But the thing is, you can apply anyways 2 by 2 pooling by somehow varying each cells their dimensions. Okay, I mean, and also you can apply either max pooling or average pooling, actually selecting 1 pixels from these regions. So you can apply max pooling or average pooling to have the 1 value from this region, and also 1 value from this region, 1 value from this region, and 1 value from this region. Anyways, you can get a 4-dimensional vector after applying this ROI pooling, okay? That fits to our purpose, okay? I mean, extract from this dimension random extracted features, we apply this ROI pooling that makes varied sized cells, and picking just one values from those varied sized cells, we can get the fixed dimensional vectors. Okay, are you guys following this? Okay, and then we can further apply MLPs to transform this to other vector, and to transform this to eventually the class semantic classes. Okay, so this is very important thing to understand the fast RCNN method. Okay, the first thing you have to understand is, instead of extracting the images, cropping the images in the image space, in this fast RCNN algorithm, they apply the feature extractor first to the whole image, and from the extracted 2D features, they actually crop the features. Then these cropped features are in different dimension according to their selective search bounding box size. They may have different dimensions, but they apply ROI pooling to make their dimension same across different size bounding boxes, and then apply MLPs to transform them to the semantic classes. Okay. And then you can feel that, this is the figures I just introduced. So they apply feature extractor, which is the ImageNet pre-trained network, image classification network. And then you can get 2D feature map, and then extract these feature maps using the selective search bounding box, and apply ROI pooling to make them in the fixed dimensional vector, and apply the fully connected layers. And actually you have to, previously I mentioned only this stream, they have to obtain the semantic class probability, okay? And we can obtain it using the cross entropy laws, right? But in this stream, what they do is they further improve, they get improved bounding box coordinate, okay? Actually, they already know that the selective search bounding box, their detailed boundaries are not accurate. So they try to further improve the bounding box, their details, okay? So actually what they do is these two things, by applying fully connected layers, they infer the semantic class probability, which might be trained by the cross entropy laws. And here they also estimate the improved bounding box coordinate that might be trained by L2 laws, but they propose another laws called as a smooth error laws. But basically, this L1 and L2 are similar, okay? So you can just regard this as the L2, the mean square error laws, okay, which might be easy to understand. Okay, and actually this is their final loss function, okay. So this loss is meaning the classification loss that estimate the semantic classes, okay. So this is the LCLS is abbreviation for the classification. So this is loss for the classification, and this is for loss for the localization, which improves the bounding box. Okay, this is easy, right? And this lambda is meaning that when mu is 0, it means the background, meaning there is no object inside the bounding box. So we apply these laws, the later laws, when there is object, if the class is not background, okay? That's represented here, okay? This is the full laws. And this is meaning the probability vector. Okay, if there is k dimension, k object classes, we have to classify them into k classes. And also this is meaning the window information. I mean, given windows, we have to somehow know their center, their coordinate. So this is center xy coordinate. Okay, this is the center's xy coordinate. And also we have to know width, height, and width. Okay, and this is two parameters for that. So when specifying one window, we need these four floating values. Okay, this is the probability for classes, and this is the window information. Okay, and the classification laws, they are similar to the cross entropy laws. Okay, and the localization laws, that's the we can somehow use the L2 laws to close the ground truth bounding box and the predicted bounding box, but they propose this smooth error laws, which looks like this. Okay, so their graph is actually like this. So they apply when the distance between ground truth and predicted values are close. They actually use the L2 laws, but if they are farther away, then they apply the Aaron laws. Okay, Aaron is, I mean, when closing the ground truth and predicted value, we can use this. Okay, this is the Euclidean laws or the L2 laws, but I mean this kind of absolute operation also could be here, and this is called as Aaron laws. This is L2 laws. This is the Aaron laws. So basically, what they do is closing the distance between ground truth and predictions. Okay, but they empirically observe that if the ground truth and predicted values, their distance are far, applying Aaron is effective, and if their distance is closer, applying L2 is empirically better than just applying L2 or Aaron. So they use the smoothed Aaron laws for that purpose. Okay, so this is laws, these formulas are meaning that, okay, so the core things in fast RCNN is this part. So they apply CNN for whole image and extract this 2D feature map and extract feature from the 2D feature map and then apply ROI pooling to make it in the fixed dimension and map it to both semantic class and also improved window coordinate. Okay. So that's the fast RCNN method. So are you guys following this? Okay. And in the same year, but later conference, the other algorithm whose name is faster RCNN have been proposed. Okay, so you can imagine that RCNN is slow, so fast RCNN, it improves its speed. At the same time, it can also improve their accuracy. Okay, but faster RCNN, they are also becoming faster, and at the same time, they are improving their accuracy. Okay, and what they do is they are actually trying to solve the bottleneck in vision proposal, which means the selective search algorithm of the fast RCNN method. Okay, I mean, you already know that these selective search bounding box, they are, I mean, obtained via using the clustering algorithm such as the k-means. But I mean, we can also estimate that using, I mean, some network. Okay, we will call that as the vision proposal network. Okay, so I mean, these bounding boxes that could be also trained somehow, And if they are trained, their activation might be even become optimal, right? And then they apply the same method as before to extract the feature level, cropping, and using the ROI pooling, make it into the same fixed dimension and map it to two things, the semantic class probability and improved windows. So the other part are same, but the thing only changed is they involve region proposal network, and in faster RCNN, they also estimate the windows, which is the object proposal, okay? So this is the comparison between these three architectures. This is the RCNN, and this is the fast RCNN, and there are another algorithm called as SPPNet, which have the similar philosophy with the fast RCNN. And also this is the faster RCNN algorithm. If you compare this, so they extract each region's feature, okay? They first extract image regions using the selective search algorithm, and they had to apply one CNN per each region. So we have to apply CNNs 2,000 times, okay? And they subsequently apply SVM to classify region-based feature, okay? That's the RCNN. And in fast RCNN algorithm, they apply one CNN on the entire image, and then extract feature from feature map regions and classify region-based feature, okay? And anyways, this is end-to-end trainable from the whole image, because CNN is can be further trained, and all these operations can be differentiable, okay? Extracting this might be applying multiplication for selective searched regions, multiply 1 to selected regions, and multiply 0 to others, maybe. So we can somehow interpret this operation as the differentiable operation and can indeed implement it in that way. So overall pipeline, from whole image to the final output, that can be fully differentiable. So in performance, it becomes better than RCNN. At the same time, they become faster because they apply just one time CNN on the whole images, okay? And here in faster RCNN, they replace the object proposal generation part using the CNN networks as well. So they remove the remaining bottleneck in this region proposal part, okay? So this is the performance comparison between RCNN, fast RCNN, and faster RCNN. And this is denoting the time taken for the inference. So for the RCNN, we have to classify 2,000 regions, applying CNNs 2,000 times. So it may take few, minute, okay? Maybe within 1 minute, we can get the result. So it seems practical because it can be faster than human ability. But when we use the fast RCNN, we apply CNN just one time to whole image and map it to semantic class afterwards using the differentiable operation. So it can be faster, a lot faster. And faster RCNN, it removes the bottleneck in this region proposal, and it becomes even faster than fast RCNN, okay? And the performance, this is two results applying the model on two different data, testing data. And this is actually denoting the accuracy whose values are better when their values are larger. So this is meaning compared to RCNN, the fast RCNN is better in accuracy, and also faster RCNN, that's also even better than fast RCNN, okay? And it's also faster than other competitive algorithms, okay? So this is the comparison and actually the history of developing object detection pipeline using the CNN architectures. And next, we will learn about the YOLO algorithm. Then maybe we will continue this on Wednesday, but I'd like to explain this. I mean, this YOLO is this RCNN algorithm. This is fast RCNN and this is the fast RCNN. So we call this as the RCNN algorithms. They are called as somehow two-stage algorithms. The first stage, they detect the bounding boxes that may contain the object inside. That's the first stage. And second, they classify each bounding box regions and map it to semantic classes. That's the second stage. So in RCNN, they are somehow divide the steps into two and first make the bounding box and classify that afterwards. So this is the characteristic of the RCNN algorithm, and they are called as two-stage algorithm. But YOLO, this is the one-stage algorithm. They at the same time achieve these bounding boxes and also achieve this semantic classification for each regions. And then they combine these two, get the final result. And they are actually, name the algorithm as the YOLO, you only loop once. And this is meaning they are one-stage algorithm, okay? And their benefit is they are very fast, okay? But YOLO is now have 11 versions. Now YOLO version 11 is there. When level upping, now the YOLO is securing the real-time speed. And at the same time, they are more accurate than RCNN algorithms, okay? I mean, at YOLO version 1 was very fast. It has the real-time speed, but their accuracy was inferior to RCNN algorithms. But from YOLO version 2, they become robust and they secure the real-time speed. At the same time, they are becoming more accurate than RCNN algorithms, okay? And maybe this Wednesday, I will continue what is their details, okay? Okay, see you next Wednesday, this Wednesday, okay, thank you.